Hi, I'm Max Hopkins. I'll be talking about solving the point location problem and active learning half spaces almost optimally based on joint work with Daniel Kane, Shachar, Lovett, and Gaurav Mahajan. So to start off, what is the point location problem? Well, given a set of hyperplanes called a hyperplane arrangement, it partitions R to the D into cells. And there's a little example down here in 2 dimensions. We have these 3 hyperplanes partitioning R2 into cells. And given an unknown point x in R to the d, here the red dot, you'd like to find what cell contains the point. Now, how can you do this? The point is unknown. Well, we're going to give you query access to the point. And what I mean by this is you're allowed to query any hyperplane H in R to the D and ask what side of H does the point lie on. So we could query this hyperplane here in our arrangement. We would get the point is below it. We could query something not in our arrangement, like this middle line here, and we'd get that it's to the right of it. And so our goal here is to make as few queries as possible to learn what cell the point is in. So here we could query the left one and the bottom one, and now we've queried the bounding hyperplanes of the cell. So we've learned that the point is here in the triangle in the middle. So there's a dual view to this problem, which is more from a learning theoretic standpoint. So in this case, we're given a known set of points in R to the D, like data points, and we're given an unknown, and we'll assume for this talk, for simplicity, homogeneous hyperplane H in R to the D. And the goal is to learn the label of your set X, of all the points in your set X, with respect to this unknown, what's essentially a linear classifier. So again, you have query access to the classifier. You don't know what it is, but you can query points and you can ask, is this point above the classifier or below the classifier? Is this plus or is it minus? And again, you don't just have to query points in your data set. We can actually kind of make up data here. We can synthesize data to send to an oracle to get a label for. And the question is, how many of these kind of synthesized queries are necessary to learn the labels of all of your points? So let's say that our universe has size n. What are some obvious bounds? Well, there's an obvious upper bound of n, right? You could just query literally every point. And there's an information theoretic lower bound that's exponentially lower. That's d log n when your points are in d dimensions. And this is information theoretic. It just follows from noticing that there are arrangements of n points in d dimensions, where by passing half spaces through different points, you can get n to the d possible labelings. And since our queries are binary or maybe ternary, if you consider equality, you have to make at least log of n to the d queries to be able to get all the different possible solutions, which is d log n. So this is how you get this d log n information theoretic lower bound. And now the big open question in this area for the last 40 or 50 years has been, can we match d log n? Is the information theoretic lower bound actually optimal? We've known you can do better than n, but can you reach d log n? So before talking about whether we can or not, I want to give a little bit of motivation for this problem from the machine learning standpoint. So the idea is that most of our algorithms that we use in practice, like deep learning, require kind of massive amounts of labeled data, which is a bit of a problem because generally what we have access to is massive amounts of unlabeled data. So, there are millions and millions of images and data and tweets, pictures on Instagram every day. But labeling this data is really expensive. So you can't just use it for your algorithms for free. It requires, querying humans to ask, is this a picture of a truck or whatever? And this is really expensive for millions and millions of pieces of data. So it's not feasible. And to get around this, for the last 10 or 20 years, there's kind of been an entire field has come up called active learning to try to deal with this problem. And what is active learning? Well, in kind of more standard passive learning, your learning algorithm will receive a batch or a stream of labeled examples. And the idea is that you want to ask, how many labeled examples do we need until we can kind of run our algorithm, until we can learn whatever the classifier is with high probability. Active learning is a little more tailored to today's scenario with big unlabeled data, where the algorithm will actually receive a huge batch of unlabeled data and an oracle, like a human, that it can query, that it can send data points to ask for the label. And the idea here is that kind of cleverly and adaptively picking data to send to the oracle, you'd hope that you can get all the labels you need for your algorithm using many fewer labeled samples. So this is very similar to the dual point location model that I talked about earlier, where the main difference is just that in our model, we're actually allowed to query any point. So we're given this batch of unlabeled data, and usually in active learning, you would just send the data to the oracle, but we're allowed to synthesize points. And this has actually been studied in the context of active learning. It's called membership query synthesis. But it's reasonable to ask, is this model reasonable? Is it necessary? If we could get away with not synthesizing points, it would be simpler and probably better in practice. So can we get away with this? And so to answer this, let's examine a very basic example, half spaces in 2 dimensions, where this is kind of a standard enough and basic enough class that your model kind of better work for this. So let's say we're given n unlabeled points in 2 dimensions, and their sign is given by some non-homogeneous hyperplane. So the inner product with some vector h and r2 plus a shift. And the goal is, given these arbitrary points x, we'd like to learn all n labels, doing something asymptotically better than the trivial solution, which is just querying all of the points. So we'd like to use little o of n labels to learn, little o of n queries to learn all n labels. It turns out you can't do this. And this has been known for a pretty long time. If the data is arranged in a circle, so in a very simple situation, the adversary can basically just cut off one point, and the learner is going to have to query basically everything, omega of n points, to find the one that the adversary has cut off. So you basically can do no better than the trivial solution. But if you're allowed to synthesize queries, so with membership queries, you can basically recover binary search. You can do O of log n, so exponentially better than the case where you basically just had to query everything. And this is because you can query things kind of outside the circle, and it gives you a bunch of extra, very informative information about where the classifier is. And so in this context, the point location question really is about asking, how does this fact that there's like this n versus log n trade-off for adding membership queries, how does this extend to higher dimensions? Can you get it to be d log n? We know how to do it in constant dimension with log n. How does it scale with dimension? So there's been a bunch of prior work on this. It started mostly on related combinatorial problems like decision trees from knapsack and K-sum. But eventually they were kind of just generally solving the point location problem for arbitrary points. And it started kind of with d to the fifth log n. And over the last 30 or so years, we've gotten the coefficient down to the exponent down to 2. So this was most recently Ezra and Sharir's work that was a d squared log n algorithm for arbitrary points. There was a recent d log n algorithm that assumed structure. So you had to have margin or bit complexity or something like that. And finally, in this work, we very nearly get to the information theoretic lower bound of d log n, assuming absolutely nothing, no structure, arbitrary point set. Okay, so let me say something about our results in a little bit more detail. We actually study two different regimes of the problem. The first is more common to a learning theoretic standpoint, which is solving the problem with high probability. So the idea is that we're going to label x with probability at least 1 minus delta for some small error parameter delta. And beyond this guarantee, we won't need anything. So we'll allow errors to be made with probability delta. It could be entirely wrong. And our measure in this case will be fairly strong. We'll measure the worst case number of queries used to do this. And the second model we'll study is much more common to the computational geometry community, which is doing this with 0 error. So we'd like to label all of x 100% of the time with no errors at all. But this is a much harder problem, and so our measure will be a little bit weaker. Our complexity measure will instead be the expected number of queries we need to do this. Okay, so now I can actually state more formally our results. So let's first look at the high probability regime. So we're saying given any arbitrary set x in d dimensions of size n, we can learn all of labels of x with probability 1 minus delta in about d log squared d log n over delta queries. So remembering the lower bound that was about d log n, this is very close to optimal. And as a corollary, you can kind of just plug this into whatever your favorite pack learner is. And it says that half spaces in d dimensions can be actively pack learned with membership query synthesis in d log squared d log d over epsilon delta queries, which is about a d factor better than anything known previously. Okay, so how do we turn this into the 0 error regime? Well, let's say we have the same setup, endpoints in d dimensions. The idea is that we'll first solve the problem probabilistically, and this will get us this first term, so d log squared d log n. And then we will take time to verify that our probabilistic solution was correct. And verifying takes about d to the 1 plus little o of 1. So our first term here is pretty much optimal, up to a log squared d factor. The second term has some room for improvement, as does the verification method, which we'll talk about later, which is very complicated. Okay, so for the rest of the talk, I want to get into what the actual techniques and what our actual algorithm is for point location. So our algorithm proceeds in rounds. I'm going to give an overview of kind of the simple structure. In each round, we're going to find a parameter k where we can learn a k over d fraction of our points by using only O of k queries. So kind of the key idea here is that we're going to couple the amount of points that we learn to the number of queries that we make in each round. So after each round, we're going to remove whatever points we learned, and then we're going to repeat the process because this kind of weak learning process for each round is going to work on an arbitrary point set. So we can just remove whatever we learned and repeat. And now because of this coupling between how much we learn and how much we query, we can show that kind of if you just repeat this process, more or less it takes about O of d log n queries to learn everything until the remaining points are empty. So, okay, what's the actual, this is the overall structure. What's the actual kind of learning framework going on behind the scenes? Well, we use a very common tactic from learning theory and machine learning, which is learning points with high margin. So margin is just kind of the margin of a point, is just how far away it is from the hyperplane. So it's kind of its distance away from the classifier. And it's kind of very well known that learning points that are further away from the classifier, learning things with high margin, is easy. So why is this? Well, let's discuss kind of a very naive basic idea. Let's say that your hyperplane H, which you don't know, the hidden hyperplane, is expressed in the standard basis as H1 through HD, and you have some point X which you do know, which is X1 through XD. And let's just imagine for the moment that you could estimate HI through some kind of queries up to error about epsilon over D. So now notice that the inner product we can write out as the sum xi hi. And so we know xi, and we've estimated hi up to error epsilon over d, which means we can actually just estimate the inner product up to error epsilon. Now, the idea here is that if we measure this estimated inner product and we get an answer that's above epsilon or below negative epsilon, because we only have error epsilon, this means that we know the sign of the inner product, which is the label. So in other words, if we measure margin greater than epsilon, we can actually infer the label. We can be 100% sure of what the label is. Now, if x has margin greater than 2 epsilon, again, because we're correct up to plus or minus epsilon, we are guaranteed to measure greater than epsilon. And like I just said, if we measure greater than epsilon, we can infer the label. So this method allows us to infer the label of any point which has margin greater than 2 epsilon. There's a bit of a problem here, which is that, I kind of made some magical assumption that we could estimate the HI. And as far as we know, we can't actually do this. But we can do something very similar. We can instead estimate the relative values of HI. What do I mean by this? Well, let's start by finding the maximum one. So we can query kind of the difference of standard basis vectors, EI minus EJ, to find which coordinate is maximum. Let's call this I star. And now for every coordinate that's not I star, for all j that aren't I star, we're going to estimate the ratio of hj to hi star by binary search. Now, how do we actually do this? Well, we'll make queries of the form the ejth basis vector minus alpha times the I starth basis vector. And why does this work? Well, let's look at what it means for the sign of ej minus alpha ei star to be greater than 0. Well, just kind of by linearity of the inner product, it's not hard to see that this implies that the ratio hj over hi star is greater than alpha. And similarly, if it were less than 0, it would be less than alpha. So now you see you can just binary search on this ratio by changing alpha and checking the signs. So, and I should note that this only takes about log of 1 over whatever accuracy you want. So again, we're only using about log d over epsilon queries to do this. So I guess you're doing it for d of them, so it takes about d log d over epsilon queries. And again, we can estimate the inner product of xh pretty much by the same way up to error epsilon. And once again, we'll learn all the high margin points. We'll learn everything with margin greater than 2 epsilon. And so once we've learned the large margin points, we can remove them. And kind of the question is, now maybe we're a little bit stuck. What do we do about the small margin points? We only know how to learn large margin points. What do we do about these? Well, the idea that was introduced a couple of years ago is to rescale these points without changing their label. So kind of if we could figure out how to rescale the points kind of in an orthogonal direction to the hyperplane without changing their label, then we could just use the large margin method again and learn more points. Now, okay, formally, what do I mean by this? Well, let's say that A is an invertible D by D matrix, and we'll define AX to be kind of the normalization of AX over norm AX. And our idea is that we're going to replace XH, so X is the points that we're trying to learn, and H is the hidden classifier, with AX and A inverse transpose H. Now, why does this work? Well, let's look at the inner product of AX and A inverse transpose H. notice it's just the inner product of xh normalized by some positive constants. So in other words, its label does not change, but its scaling does change. So it's exactly what we're looking for. And moreover, we can actually simulate these queries, because remember, all we're ever actually interested in is the sign of these inner products. And so if we just normalize x by norm of ax, everything, all the points are kind of globally scaled by this A inverse transpose H that we don't know, but because global scaling doesn't affect sign, we can simulate the queries just by normalizing by AX norm inverse. Okay, so what's the idea here? I said we want to scale in the orthogonal direction, but we don't really know what the orthogonal direction is. So instead, the idea is to kind of stretch in every direction. So that kind of no matter what the hyperplane ends up being, you'll get some success in that direction. And this is really called putting points into isotropic position. So we prove a theorem in this work where as long as your set is not too degenerate, we show that you can transform it, that there exists an invertible matrix A that transforms X into isotropic position or approximate isotropic position. Okay, so what is isotropic position? Well, a set Y is an isotropic position if for any unit vector in R to the D, its average margin, squared margin in that direction is about 1 over D. So about for the approximate case, exactly if you wanted exact isotropic position. And what does it mean to be degenerate? When can't you do this? Well, it's fairly intuitive. You can't do this kind of when there's a subspace, when there's a direction that your points are too dense in, when too many of your points lie on some subspace. And the idea is that kind of linear transformations preserve subspaces, so you kind of can't symmetrize in this direction. You're going to have too much weight stuck in this direction. And so in particular, it's if you have a k-dimensional subspace with a greater than k over d fraction of your mass, you can't do this. The proof of this builds on some old work in vector scaling by Barta, Forster, Carlin, Lieben, Loss, and Dviersvov and Vigderson, and more or less with a bit of work, the theorems implicit in the last two of these. Okay, so what does isotropic position actually mean for margin? I said that we're kind of stretching it in every direction. So naively, what you can say is that isotropic position guarantees that a 1 over d fraction of your points have big margin, have margin at least 1 over root d. And we're assuming here that x are unit vectors, but we can scale without loss of generality. So that's fine. And now let's say we just naively applied our old approach. So we went through, we isotropic transform our points, we learned the 1 over d fraction of x that has large margin, and we repeat. This takes about d squared log n queries, which matches the previous best known algorithm, but isn't good enough for us. We'd like to hit the information theoretic lower bound. We'd like to do d log n. So how can we get rid of this extra d that we're dealing with? Well, the idea is to look at the structure of margin beyond the first 1 over d points. So we're going to look at two cases. Kind of in one case, all or almost all of the margins in X are large. Kind of you go along X looking at its margin, and it never really decreases by too much. And the second case is that you're kind of going along the margin, and then there's a sharp drop. Over a short period of time, the margin drops by like a polynomial in D factor. And in this case, we're going to figure out how to actually reduce the dimension of the problem. Okay, so let's go over what do we do in these two cases. Well, in the first case, most of the points have large margin, and this is kind of the easy case. If we just use the naive strategy that I told you about before, it actually infers a constant fraction of x in O of d queries, and we're okay spending O of d queries, remembering kind of this, that we're coupling the number of points that we learn to the number of queries that we make. If we learn almost all of x, we're okay with making O of d queries. Now, the second case is more difficult, and we're going to try to figure out how to reduce the dimension of the problem. So in this case, your formal guarantee is that there exists a gap in margins where let's say that x1 through xn are sorted by margin. You know that the first kn over d points are kind of large. And after point 2 kn over d, everything is really small. It's much, much smaller than the first kn over d points by like a poly d factor. So you might notice this k parameter here is very similar to the k that I was talking about in the algorithm overview that we're trying to find to learn a k over d fraction of points. And here we have a k over d fraction of large margin points. And indeed, this is going to be what we're going to do. We're going to try to reduce to k dimensions and learn these large margin points in k dimensions. Now, how are we going to do this? Well, let's take a look at what the approximate span of the small margin points look like. So first of all, because the set is an isotropic position, we can prove that this approximate span has very large dimension. It has dimension about d minus O of k. And moreover, because the points in the space are kind of an approximate sum of these small margin points, as long as their norm is small, they also have very small margin. And so what's the idea? Well, our dimension reduced space will actually be V perp. So the idea is let's project all of our points onto V perp and just apply the naive algorithm. And why does this work? Well, because V is all small margin, V perp basically accounts for almost all of the margin of our points. And further, V perp is O of K dimensional. So applying the naive algorithm only takes about O of K queries. So as long as we can kind of verifiably find V perp, we'd be done. But okay, so here's an image to maybe clarify things, because that was a lot of words. So here in black, we have our hidden hyperplane. We take V, the red line, to be the approximate span of these small margin points near the hyperplane. And we take V perp to be, it's perp line. And I show here kind of projecting this one blue point onto V perp. And you see it doesn't cross H. Its sign doesn't change because it's, fairly far from the hyperplane. So anything that's far out, anything that has high margin, we can project onto VPerp and apply our naive algorithm to learn. So the challenge then is, how do we actually find VPerp efficiently? Remember, in each round, we're only allowed to use K queries, about K. Okay, we certainly can't, query every point and find its margin, but we could approximate V with a small random sample. And we need about O of D points to do this to preserve its structure. And again, so we run into this problem. We need O of D small margin points, but we can only make O of K queries. How are we going to deal with this? Well, one idea is to kind of test batches of points probabilistically to see if they all have small margin. And to do this, we introduce, I guess, a new query we call approximate maximum. And the idea is, given a subset of your points, approximate maximum will output one of the points in the set that is almost has the maximum margin. So it's only about a 1 over S factor off from whatever is the maximal margin of your set. And the idea here is that if you, let's just say you have this query, we don't know how to do it yet, but let's say you have this query. You could draw samples of size about D over K. You could draw about K of them. And you could make the query, and you could just check that whatever it outputs is far less than your large margin points, and the margin of xkn over d, which is our large margin point. And then because you're reasonably close, you're only off by like a 1 over d factor, and the gap is much bigger than 1 over d. It's like 1 over poly d for some larger exponent. You can be guaranteed that your entire sample is small margin points. You can find a bunch of small margin points in very few queries by doing this. Now, of course, there's a problem, which is that we don't come equipped with an approx max query. We're going to have to simulate it. And this is where the probabilistic component of our algorithm actually comes in. We're going to probabilistically simulate approximate maximum by taking random Gaussian combinations of kind of subsets of S and cleverly comparing them to each other. I'm not going to go through the details of it, but you can look in the paper if you're interested. It's not too complicated. Okay, so assuming we can do this, we can probabilistically simulate approx max. Then we're actually done. So let me go over the algorithm in more detail now. We start with all of our points x0, and then while xi, kind of our iteratively updating set of remaining points, is non-empty. If it's non-degenerate, we'll isotropic transform it. If it is degenerate, well, we can find a subspace that's very dense. And the idea is we'll basically just restrict to this subspace that's dense. And we've lowered the dimension while keeping kind of a large fraction of points. And we'll just check if this can be transformed. If it's not, it's degenerate. And you just repeat until you either hit one dimension where things are necessarily isotropic, or you find something you can isotropic transform, and then we'll just work over that. Okay, so the idea is you now find some ki and vi for whatever your transformed set of points are, probabilistically using only O of k queries. And now we project onto vi perp, and we learn a k over d fraction of x in only about O of k queries. So we get this coupling behavior where we couple the number of queries we make to the number of points that we learn. And now we just repeat until xi has nothing left. And like I said before, this kind of model only takes about d log n. So we've solved the probabilistic method with the probabilistic regime. Now, how do we actually verify that we didn't make any errors in this procedure? Well, errors occur when approx max fails, when our probabilistic simulation testing small margin points fails, and they aren't actually small. So what we need to verify is that a bunch of small margin points that we use throughout the process, possibly d squared of them, are actually small margin. And this is a little bit difficult to do. And the way that we do it is we break it down into smaller, lower dimensional point location problems, and then we solve recursively. And this ends up taking about d times 2 to the square root log d queries, which is non-optimal. And it uses the internal structure of our weak learner. So it's very complicated. Okay, so this kind of leads well into what open problems are left. The first is kind of making a better verification technique. Kind of, can we use our weak learner as a black box instead of using its internal structure? Can we, given that probabilistically we know the correct cell, can we verify it in L tilde D queries, O tilde D queries? And the second is de-randomization. Kind of our algorithm is randomized. Previous de-randomization techniques fail, and they actually also have a little bit of blow up. And so kind of it's very open how you would de-randomize this and get a deterministic algorithm for point location. And that's everything. Thanks.